To find sample size, we can reverse cook up this business about the margin of error and solve for the sample size n. That will give us a minimum sample size to be within a specified margin of error. If we do that backward, we can solve for that value of n. Like I said, you don't have to do it. It's been done for you. So the p times 1 minus p times the critical value of z divided by the desired error, all squared. Now we have some choices for p here. P would be the proportion that we're trying to estimate. If we have a prior estimate, p hat, then we're going to use that. If, however, we don't have a prior estimate, we're running a new inquiry, or the prior estimate that we have we think is invalid, then we use 0.5, 50% chance, 50-50. We have no idea, we just like smack it right in the middle like that. That maximizes the possibility of it going either direction. So we use 0.5 for p if no prior estimate exists, or the one we have we don't like and we don't want to use it. Then we always round up just to make sure that our sample size is large enough. So that's our formula. All it is now is just plugging it in there. An economist wants to estimate the proportion of Americans who own their home. What sample size should he use? So now we know, so what size sample, what is the value of n? If we want to be within 0.02, that's the error, and 90% confidence, so that's the confidence level. The confidence level tells us the critical value of z that we want. For 90% it's 1.645. So from this formula, the sample size n is the proportion, if we have a prior estimate, which we do in part A, times 1 minus the proportion times the critical value of z divided by the error, all squared. So here he said in 2010 there's a census thing that said about 67% of people own their home, so let's start there. Like, that's a good place to start. Granted, that was 6 years ago, but at least it's something. Then we have 0.669 times 1 minus 0.669 times the critical value of z, 1.645, divided by the acceptable error, 0.02, all squared. That gives 1498.04 as a sample size. Like I said, always round up. This 0.04, we can't sample 0.04 of a person, so we'd go up to the next integer. Make sure that we capture that error and that level of confidence. Nobody would really sample at 1499. That's what we get back. We'd aim it at an even 1500 probably. But now we know the minimum sample necessary to get within this margin of error of 0.02%. If we do not use prior estimates, so for whatever reason we don't think that this value is accurate anymore, then we'll use that p is 0.5. 50% of people own their homes or not. That will maximize this minimum sample size necessary. So n equals same formula, p times 1 minus p times the critical value of z divided by the acceptable error, all squared, but now p is 0.5, so 0.5 times 1 minus 0.5 times the critical value of z, 1.645, divided by 0.02, all squared, gets a minimum sample size of 1691.26, which is 1692 to the next integer. Even though both of these numbers were small, 0.04 is very tiny, we still need to round up. So herein lies the difference between sample sizes. If we use a prior estimate, we were about 200 less in the minimum sample size than if we have no idea where we're starting. Larger samples are always better, but they aren't always the most economical or possible. We don't have the kind of funding for that. So if we can use a prior estimate, we can get a little bit closer and make the number of individuals we want to look at smaller, which can save money and time, but it might not get us where we need to be.